11.3 Integral and Comparison Test. In general, it is difficult to find exact sum of a series. We did this for the geometric series and for 1 over n times n plus 1. And we found a simple formula for S of n. In this section, we will look into tests that will determine convergence or divergence without explicitly finding the sum. So let's recall an important theorem called the monotonic sequence theorem. Monotonic sequence theorem, which says that every bounded monotonic sequence is convergent. So we have two conditions for convergent, and that is bounded and monotonic. Monotonic meaning increasing or decreasing. So here we deal with series with positive terms. So here we deal with series that have positive terms. Therefore, the partial sum is increasing. So partial sums are increasing. So we have the first condition, the increasing part. So we need to determine whether the partial sum is bounded or not. So we need to determine whether the partial sum Sn is bounded or not. If it is bounded and it's already increasing, so it's bounded and monotonic, so it's convergent. So number one, testing with an integral. Testing with an integral. Let's look at this sum, 1 over n squared. N is from 1 to infinity. And let's expand it, 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, and so on. So if we calculate the partial sums, I will make a table here for n and the partial sum Sn, which is sigma 1 over I squared, where I is from 1 to n. So if n equals 5, and add the first 5 terms, we're going to get approximately number 1.4636. If n equals 10, we'll get 1.5498. I'm going to write a few more so we can see a pattern. If n is 50, 1.6251, and continue here is n is 100, 1.6350. If n is, we'll continue here. If n is 500, 1.6429. For 1,000, 1.6439. Obviously, we use technology to calculate this. Oh, I have one extra zero here. So this is just 1,000. Let me do this again. 1,000. And then from 5,000, we have 1.6447. So we notice here, as n goes to infinity, what is the partial sum Sn going to? We can safely assume it looks like it goes to 1.64. Okay, so it appears it's the, convergent. Now we can make a geometric argument as well. This is not a proof, but it is an argument And the geometric argument will use areas to add those terms. So our function y equals 1 over x squared, because we are adding 1 over n squared. So if I use that function, and this is 1 right here, the first term is 1 over 1 squared, which is 1, which will be represented with this area. This area is equal to 1, which is represented with the first term in a series. So I can mark 2 over here, and this rectangle will represent the area. The area of this rectangle, it's 2 times 2. The area here is 1 over 2 squared. Because the length of the rectangle is 1, that's how we made it. The height is the value of the function, so it's 1 over 2 squared. So the area is 1/4 basically. The next area here, should use different color. So this area is the second term. This area here is the third term, 1 over 3 squared, and so on. This is 4. This rectangle area represents the next term, 1 over 4 squared, and so on. So let's exclude the first rectangle, which is a square, the 1 with area 1. So exclude, just for convenience, exclude the first rectangle, which is as a square actually. 1 by 1. Okay, so we're going to exclude this one, and then the total area of the remaining rectangles is less than the area under the curve for x greater or equal than 1. And that area under the curve is exactly equal to integral from 1 to infinity 1 over x squared dx. So let's see it out on the picture. So we have what we just said, that the total area of the remaining rectangles, so this area of this rectangle, and this one, oh, shouldn't go outside here, this one, and so on, the sum of those areas is less than the area under the curve, which is a definite integral. So we know that integral from 1 to infinity 1 over x squared dx is improper, but it is convergent. And this is how we're going to find the sum, or this what this integral is equal to. Integral from 1 to infinity 1 over x squared dx, we write it as a limit from 1 to t goes to infinity 1 over x squared dx. And now we're going to evaluate it. This is the limit. Think about x to the negative 2, antiderivative negative 1 over x from 1 to t, and t goes to infinity. So evaluate this, and you get exactly 1. So this integral is convergent, and it's equal to 1. So our partial sum, Sn, which is the first n term, is less than 1 over 1 squared, that's the first rectangle, plus area under the curve, which we know is equal to 1, so that's 1 plus 1 equals to 2. So Sn, the partial sum, is bounded. Why is it bounded? Because we just found it's less than 2. Therefore, okay, therefore our series 1 over n squared and from 1 to infinity is convergent. And the sum is less than 2 and has sum less than 2. Okay, so let's write down, we have the result here. Now Euler later found that this sum, he calculated exactly this sum for n from 1 to infinity, that is pi over 2 over 6. So now let's look at another example with a sum 1 over square root of n. N is from 1 to infinity, and let's expand it. 1 over square root of 1 plus 1 over square root of 2 plus 1 over square root of 3, and so on. If we make a table again for the partial sums, like before, n and the partial sum, we're going to see that for 5, we get 3.2317. For 10, we get 5.0210. For 50, for 100, 500, 1,000, 5,000. So if we look at those numbers, the first thing we notice that those partial sums are increasing. And they don't seem to approach a specific number. This is approximately. So we suspect this series is divergent because it obviously, even though it goes slowly, but it is increasing, so it goes to infinity. Now let's see the geometric argument. So just like before, we have the graph of our function. In this case, that is y equals 1 over square root of x. And for 1, 2, 3, and 4, we're going to construct the rectangles. So for the first rectangle, we see the rectangle is outside. It's above the curve. So we know what's going to happen. Then the sum of those areas will be bigger than the area under the curve. So this first area is equal to 1 over square root of 1. This area is 1 over square root of 2. And this area is 1 over square root of 3, and so on. So we have more rectangles here. But what we notice, the rectangles, all of them, the rectangles are above the curve. So our sum appears to be greater than area under the curve, which is integral 1 over square root of x dx from 1 to infinity. Now, what do we know about this integral? So this integral, which is improper, let's rewrite it as x to the negative 1/2 from 1 to infinity. Actually, I will leave it as 1 over x to the 1/2 from 1 to infinity. And if you recall from a previous chapter where we have integral of this type, 1 over x to the p, this integral is convergent if p is greater than 1. So we had that learned previously. So if we use this, then we can say, in our case here, this is divergent because p is less than 1. It's 1/2. So this is divergent. So we can say now that our series, the series sigma 1 over square root of n, and from 1 to infinity, is divergent. So we're ready to state the integral test, or how we use an integral to determine if a series is convergent or divergent. So the integral test has some conditions. F has to be continuous, it has to be positive and decreasing on the interval from 1 to infinity. So let a sub n is equal to f of n, then the series sigma a sub n and from 1 to infinity is convergent if and only if the improper integral which is integral from 1 to infinity f of x dx is convergent. In other words, let's restate this. In other words, A, if the improper integral from 1 to infinity f of x dx is convergent, then the series is also convergent. And B, if the improper integral f of x dx is divergent, then the series a sub n is divergent. So we have this connection. If the integral is convergent, the series is convergent. If the integral is divergent, the series is also divergent. So some notes here. Note, when we use the integral test, it is not necessary to start the series or integral with n equals 1. So when we use the integral test, it is not necessary to start, I'm just going to say to start with n equals 1, meaning to start the series or the integral. Example, if I have this series 1 over n minus 3 squared, and n is from 4 to infinity, for this series that doesn't start with 1, we use an integral that doesn't start with 1. That's okay, as long as the lower bound is some constant finite number. Also, another note, it is not important that f is always decreasing. It is not important that f is always decreasing. But it is important that f ultimately decreasing is ultimately decreasing. In other words, it's eventually decreasing. So I'm going to write down it's decreasing for some x greater than n, where n is a finite number. Then this sum, sigma a sub n, and from big N to infinity, then this being convergent leads to our series a sub n, but now from 1 to infinity is also convergent. Okay. So if we remove a few terms from the series, finite terms, it's okay. it doesn't make a difference. Example, determine whether sigma ln of n over n, where n is from 1 to infinity, is convergent or divergent. So the corresponding function here is ln x over x, and that is a positive function, which was one of the conditions for the integral test. It is also continuous for x greater than 1. So we need that from the natural log. Not clear, however, whether f is decreasing or not. Not clear whether f is decreasing or not. So this was our last condition. If you go back to the integral test, let's highlight it here. This is our integral test. And it was important to note the conditions: continuous, positive, decreasing. Okay, so 3 conditions. So let's go back here. We had positive, we have continuous, not clear if it's decreasing. So one way to find increasing or decreasing is to compare to consecutive terms. It will be difficult with our function, with our sequence to do this. Another way is to look at the first derivative. So f prime of x, if we use the quotient rule, we can find f prime of x, and if we can find where it's negative, and that's where f will be decreasing. So let's do the quotient rule here. 1 over x times x minus ln x over x squared. We simplify 1 minus ln x over x squared. So the denominator is always positive. So that's not interesting. We just need the numerator. In order for f prime to be 0, we want to make sure that 1 minus ln x is negative, which is equivalent to ln x greater than 1, which is take everything e to the ln x greater than e to the 1, so x greater than e. So we found that for x greater than e, f is decreasing. Okay, so this is a third condition, so we apply the integral test by writing the integral, improper integral, ln x over x dx, and we're evaluating it by setting a limit. T goes to infinity, 1 to t, ln x over x dx, which is limit t goes to infinity, integral, I'm going to write this ln x of d, ln x, or you can use a substitution from 1 to t, and evaluate this. This is, the substitution will be ln x equals to u. And evaluate it, ln x squared over 2, evaluate from 1 to t, and t goes to infinity. We're going to do the limit at the very end. So now, evaluate the top boundary, so it'll be ln t squared over 2 minus ln 1 over 2 squared. So now, this integral is a constant, I mean ln 1, that's 0, but this one goes to infinity. So this one goes to infinity. So what we have by the integral test, if the improper integral is divergent, then our series ln n over n from 1 to infinity is divergent. So the series is divergent because the integral, the improper integral, was divergent as well. So another example, for p equals what, the series sigma 1 over n to a power p, and from 1 to infinity, is convergent. So let's explore the different possibilities for p. So if p is negative, we have limit of 1 over n to a power p. P goes to infinity, and that goes to infinity. If p is 0, so think about p in the first case, p negative. 1 over n to a negative power is n to a positive power, so that goes to infinity. Now if p is 0, we have 1 over n to the p, and we know anything to a 0 power is 1. So in these cases, in both cases, we have divergent series. Divergent because the nth term, which is equal to 1 over n to the p, does not go to 0 when n goes to infinity. That should not be in red. Okay. So the nth term did not go to 0 from the test for divergence. If you recall, 11.2 tests for divergence. So in the first case, the nth term goes to infinity and then to 1, which is not 0. So we have divergence here for p less than 0 and for p equals 0. Now, if p is positive, then our function f of x is 1 over x to the p. That's continuous, positive, and decreasing from 1 to infinity. And then the integral, the improper integral, 1 over x to the p dx is convergent if p is greater than 1, and divergent if p is from 0 or less or equal than 1. So this series, very famous, it's called the p series. Sigma 1 over n to a power p, and from 1 to infinity is called p series. And so the result summary is the following. The p series, sigma 1 over n to the p, and from 1 to infinity, is convergent if p is greater than 1, and divergent if p is less or equal than 1. This is very important, this result summary about the p series, because we're going to see examples of p series often, and knowing this will help us determine convergence quickly. So example, sigma 1 over n to the third, and from 1 to infinity. We recognize this is a p series. Let's expand it. 1 over 1 to the third plus 1 over 2 to the third plus 1 over 3 to the third plus so on. So we say this is convergent because it is a p series, and p is greater than 3, which is p is 3, which is greater than 1. But here's another example. Sigma 1 over n to the power 1/3, n from 1 to infinity. We can expand that as well. We can write it as 1 over cube root of 1 plus 1 over cube root of 2 plus 1 over cube root of 3, and so on. This is divergent because p is equal to 1/3, which is less than 1. And that concludes part A of this video.